will speak Professor Sidong from University of California, Santa Barbara. He is also recipient of the Frontiers of Science Award 2024 in the field of string theory and gravity. He will talk about the award work. The title is about locality and error correction in holography.
Thank you. I'm very honored to be here today to have the opportunity to give this talk. I'll tell you about how to understand quantum gravity from the seemingly unrelated idea of quantum error correction. So understanding quantum gravity has been a long-standing goal of theoretical physics, going back many years. And by now, we have two precise theories of quantum gravity. One is called the anti-de Sitter Conformal Field Theory, or ADS-CFT correspondence. And the other set of models are called matrix models. Both of these two kind of theories of quantum gravity have the property that they are holographic, in the sense that the fundamental description of the theory actually lives in fewer dimensions than the effective gravitational description. For example, in ADS-CFT, we have gravity in a d+1 dimensional bulk that is described by a CFT on the boundary, so in a d-dimensional boundary. But I will define ADS-CFT a little bit later. But now, all that is important is that it is something that is holographic. So this leads to two natural questions that we can ask. One is that why should quantum gravity be holographic? Why should this be true? Why should this work? And the second is, how can this work? How can a lower dimensional theory somehow describe gravitational physics in higher dimensions? So in this talk, I will first review the answer to the first question, why should quantum gravity be holographic? And then describe a relatively new and precise way of thinking about the second question in the context of the ADS-CFT. So first, I'll review the answer to the first question, why should quantum gravity be holographic? And one special thing about gravity is that it prevents us from defining the kind of local observables that we are familiar with in quantum field theory, like QCD or QED. The rough idea is that if we try to define this kind of local observables in such a theory, gravity prevents us from doing that because whenever we're trying to do things that are very precisely, eventually we form a black hole and we won't be able to probe the precise local structure. This tension is most sharply illustrated by the black hole entropy given by the Bekenstein-Hawking formula. And this is very extremely beautiful formula that involves all the important constants of nature. And if we set them to 1, then we're left with A/4. So the important thing is that this is entropy that scales like the volume, say like the area, not the volume. So it's not extensive. And the answer to the first question is that in holography, the lower number of dimensions is what is precisely needed in order to get this entropy right. The entropy scales like the area, not as a volume. So if the fundamental description lives in a lower dimension, then it matches with the entropy tells us. So this answers the first question. Now, we move on to the second question. How could a lower dimensional theory actually describe a higher dimensional gravitational physics? And to do this, I need to say a little bit more about ADS-CFT. So ADS-CFT is a duality. What it says is that quantum gravity in an asymptotically anti-de Sitter space, which is anti-de Sitter space is the simplest space with negative curvature. In such a space, if we have quantum gravity, the theory is completely equivalent to a theory in lower dimension on the boundary of the anti-de Sitter space, living on and has no gravity. So it's a conformal field. This is a concrete example where space and space-time gravity emerge from a non-gravitational system. The CFT is a non-gravitational system, but somehow gravity emerges from such a theory. And when I point at these, maybe just to say a little bit what this picture means. The cylinder, the solid cylinder is where the gravitational theory lives. It lives in the interior. There can be observers inside. But the dual description just lives on the boundary, which is the cylinder here, and has no gravity. So a concrete example of such a duality is, in fact, the first example is Type2B string theory on some kind of ADS5 manifold cross another S5 in the most simplest examples. That is dual to a particular kind of super Yang-Mills theory with a gauge group SUN. And it's supersymmetric. So this is certainly a toy model for quantum gravity in the sense that our universe is not anti-de Sitter. So even if we can understand everything we want in such a setting, we're not done. We still need to understand quantum gravity in our universe. But this serves as a good toy model that we can extract lessons from. And if we understand such a toy model, we can eventually apply those lessons to understanding quantum gravity in our universe. And that's our ultimate goal. So it's a duality. Just to say a little bit more about what we know about this duality, we know, well, since it's a duality, there's a one-to-one correspondence between the states on one side to the other. So each bulk state is in principle mapped by the duality to another, to a boundary state in the CFT. Operators can be mapped from one side to another as well. For example, the Hamiltonian and other conserved charges like angular momentum are mapped from one side to the other. The Newton's constant on one side certainly is mapped to something else, is mapped to 1 over n squared in a simpler setting in the CFT, where n is the rank of the gauge group. Roughly speaking, n describes how many degrees of freedom we have on the field theory side. And finally, we know something about how to map operators from one side to another. If we take a local field in the inside anti-de Sitter space, the corresponding thing that we can get to go to the CFT side is to take the operator phi and then pull it to the boundary. So take a limit where the radial coordinate r goes to infinity. That's approaching the cylinder on the boundary. And if we take a particular scaling limit, it approaches some kind of local operator in the CFT, which we can call O of x. So using these rules, we can do scattering experiments, ADS-CFT. And they're described by simply CFT correlation functions. For example, we can imagine doing this kind of scattering amplitude. And in a very rough setting, we can think of this as being given just by calculating the 4-point function in the CFT. We can do many things of this kind and many scattering experiments. But the question I want to ask is, can we go beyond those scattering experiments and describe physics that is going on truly inside the bulk, for example, near the center of ADS? Can we do this? And I want to provide some motivation for why I'm asking this question. There are two empirical reasons why we want to do this, talk about physics really in the bulk, as opposed to just talk about the kind of scattering experiments given by this kind of 4-point functions. And the first one is cosmology. This is the first motivation for why we ask questions about the bulk by itself. Our universe seems to have recently entered a period of rapid exponential expansion. We think that is driven by the cosmological constant. In such a universe, we think that there is no scattering experiment that we can do because everything we can see is confined within a finite volume. Beyond that volume is outside our cosmological horizon. So it does not immediately make sense to talk about the scattering experiment in this setting. So this is cosmology. A second motivation for why we think we should not be satisfied with just talking about scattering experiments is that black holes exist. And in particular, if we have an infalling observer that goes across the horizon, goes inside a black hole, such an observer is interesting in the sense that it only has a finite amount of space and time to do experiments. You can talk about measurements before it hits the singularity, but that's a finite amount of time, proper time. And there's only a finite amount of space as well. So there is no scattering experiments for those infalling observers. And it's a very interesting question. How do we describe their experience? And importantly, this is not just a conceptual question, but also could be a practical question in the sense that we can imagine a situation where Alice and Bob live in different universes, and the only way for them to meet each other is for them to each jump into a black hole that the two black holes are connected by a wormhole, and they can hope to meet in the interior. And if they time their arrivals well, in this setting, there is no scattering experiment to describe such a meeting in the interior. But nonetheless, we'd like to understand whether or not they meet. So I want to point out that this second motivation is not completely independent of the first, the motivation from cosmology. In fact, I think that understanding this interior of the black hole could shed important light on how we understand cosmology. So having said these two motivations, now I want to focus on the concrete question in the remainder of this talk, which is how is the physics in the middle of the space, and in particular ADS space, encoded in the fundamental degrees of freedom describing quantum gravity? And since ADS-CFT is our best understood example of quantum gravity, I will use this as the context where I answer this question. And in particular, it's a duality. So one might try to just write down some equations describing an operator in the middle of the space in terms of the fundamental degrees of freedom, which are CFT operators. So try to write down a bulk operator in terms of CFT operator. And this turns out to lead to a paradox in the following sense. In quantum field theory, causality is usually enforced by locality, the statement that two operators commute when they are space-like separate. Quantum field theory, this is definitely true. We might expect this to hold also in the bulk. In the bulk, we expect quantum field theory to be a reasonably good approximation. And certainly in our real world, operators commute to very good accuracy, even though we have gravity. So we might expect that phi in the bulk in the center commutes with O on the boundary as long as they're space-like separated. For example, if they are on a single time slice. But actually, this is impossible to be precisely true in the boundary CFT. Once we map this phi operator to a boundary, this is a paradox. It has to do with what is known as time slice axiom of quantum field theory. This axiom says that any operator that commutes with all local operators at a fixed time must be a trivial operator, in other words, a C number. It's important that this statement holds for any operator that you can imagine, not just local operators, but non-local operators as well. In other words, if you look at the set of all local operators in quantum field theory, that set on a single time slice should act irreducibly on Hilbert space. This is the same statement as the axiom. So what this means is that if phi commutes with all the O's on a single time slice, according to this axiom, phi should be a C number. But obviously that is not true. We can compute correlation functions. They are not C numbers. We know that they are not trivial. But then the question, of course, is how can we solve this paradox? How can the extra dimension emerge despite the fact that we have the time slice axiom in the quantum field theory? To make this issue even sharper, you can actually write down a formula for representing such bulk operators in the quantum field theory on a boundary. This goes under the name of Hamilton, Tabat, Lifshitz, and Lowe, so HKLL. And the formula looks like this. So you have a bulk operator phi in the center or somewhere near the center that you want to write in terms of a CFT operator. And at leading order, it is given by an integral of a smearing function K times the boundary operator O. O is the boundary operator that is dual to a particular bulk field phi. And this is called bulk global reconstruction in the sense that in one way of doing this, the support of this integral is in this green region. The green region is to be thought of as a band on the boundary, consists of all boundary points that are space-like separated from the bulk point you are trying to reconstruct. So this is global in the sense that it involves the entire time slice of the CFT. We'll see something that is more local in a moment. And this is a formula that works at leading order in the larger limit, but nonetheless, 1/n corrections can be incorporated if I add more terms to this equation. So, this makes the previous commutator puzzle even sharper in the sense that now we have a formula that writes the bulk operator in terms of boundary operator. How can we find the how can we make peace with the time slice axiom is one puzzle that we have. But before solving that puzzle, which I call the commutator issue, let me introduce a second paradox, and we'll solve both of them at the same time. To introduce the second paradox, there's one technical tool that is needed, which is a more subtle version of the reconstruction that happens on a subregion. So the idea is that you can write down almost exactly the same equation for representing a bulk field phi in terms of an integral of a smearing function times O, but now the support of the integral is much smaller. The support is only on this green region that is much smaller than the global band that I had on the previous slide. This turns out to work for, so the way that this works is one is to choose a particular A, which is this, so let me say a little bit more how to choose this. So on a single time slice, which is a circle in this picture, you divide it into a segment A and the complement A bar. And then on a boundary segment A, on the boundary, you can define this causal diamond, which is the green region that the integral is integrated over. And this kind of integral doesn't work for all bulk operators that you can imagine putting in the bulk. It only works for a particular set of bulk operators that are located in the Rindler wedge. The Rindler wedge can be roughly thought as being given by this wedge where you construct 45-degree planes coming from the boundary and then intersect at an extremal surface. And everything that is inside this wedge can be reconstructed by this equation. Anything outside cannot be constructed by this kind of equation. So this is called the Rindler reconstruction. And this Rindler reconstruction and the previous global reconstruction are related in the bulk by a simple Bogoliubov transformation. But the point is that the Rindler reconstruction is more powerful. For example, if you want to compute expectation value or correlation functions of such phis, in the Rindler reconstruction, all you need is the state of the CFT on the region A. You don't need any information about the state on the complement region, because what you can do is to, instead of taking an expectation value on the global state, you can write a trace of a product of phis times the density matrix on A. And since the reconstruction is supported on A, you can do that calculation just by knowing the state on A. So it's using a very limited set of CFT data as compared to the previous slide. In that sense, it's more powerful. Now, this is a kind of a subregion duality because we're doing duality on a subregion, not on a global slice. And this is very important. So let's also look at it from above on a single time slice. It basically says on a single time slice, we have A and this complement, and operators that are in the shaded region, for example, this particular phi of x, can be reconstructed as an operator on A, but operators outside the shaded region, for example, this operator phi of y, cannot be reconstructed on A. In this picture, phi of x, phi of y, the operator to the right in the unshaded region can actually be constructed on the complement of A bar. So now we're ready to phrase the second paradox. The paradox is, imagine that I look at the whole boundary on a time slice. So it's a circle, and then I divide it into three thirds, A, B, and C. And if we look at an operator in the center, because it's outside this wedge of A, Rindler wedge of A, it cannot be reconstructed of A. it is outside the Ringler wedge of B, this shaded region, so it cannot be reconstructed on B. Similarly, it cannot be reconstructed on C individually. But nonetheless, if we consider the union of A and B, then the Ringler wedge is much bigger. Now it includes everything that is up to this line, and it includes the center operator. So the operator in the center can be represented as an operator on the union of A and B. And similarly, by symmetry, it can be represented on the union of B and C and the union of A and C. So it has at least these three representations. We can call these three different representations phi AB, phi BC, and phi AC. The point is that as CFT operators, they cannot be the same operator in the CFT. They manifestly have very different support. Locality of the CFT shows that they must be different operators. That raises the question of where is information actually located that it describes the center. So how can we make sense of the three different ways of writing down a central operator? So we have now two sharp paradoxes. One is that the bulk operator in the center seems to commute with all local operators of the time slice, but on the other hand, it's not a trivial C number, so that seems to be in contradiction with the time slice axiom. The second is that the same operator in the center seems to be constructed, represented by three different operators on the boundary that are not the same. So it's now understood that both of these two puzzles can be solved by interpreting ADS-CFT as a quantum error correcting code. And let me first explain what quantum error correction is. Quantum error correcting codes are devices that we think of that was invented to do computations despite decoherence. So if we imagine a quantum computer and doing computations, there can be errors, noises from the environment. And we would need to protect such quantum computers from those noises, and quantum error correcting code is a way to do that. It's very similar to how in classical computers, we also need classical error correction inside your computer memory in order to make sure that computations are ever free. So the basic idea is to protect quantum information or quantum message by not storing it locally, because if we store it locally, it's easily corrupted by a local erasure or some other noise, but rather encode it non-locally in the pattern of entanglement between different parts of the system. And because it's stored non-locally, it's then much harder to try to destroy it using noise. And there's a general theory of quantum error correction that I can tell you about, but instead, I want to just focus on a simple example to illustrate how that works. So the simplest example I find that illustrates this in this context is called the putrid model. The goal of this model is to demonstrate how I can send you a single putrid state in a way that can be protected from corruption. So this putrid state is simply a state, arbitrary state, in a three-dimensional Hilbert space. So it's a linear combination of three basic states, 0 and 1 and 2. So it's called putrid because it has three states. Very roughly, you can think of a three-level system if you want, but this is the state we're going to send. Suppose I want to send it by mail, and we know that mails can get lost or corrupted. So if this were a classical message, I could do something very simple, just by sending you many envelopes containing many copies of the message. And as long as you receive one of those envelopes, you're done because you can recover the information. In quantum mechanics, I cannot do this because there's no cloning theorem. So the actual way to do this is to instead send you a state that involves three Q-trids, not just one, where the three Q-trid state is we're sending a state that is given by a same linear combination of three special three Q-trid states, where this K tilde is a state in the three Q-trid Hilbert space. So it's a 27-dimensional Hilbert space. But there are three special states, 0 tilde, 1 tilde, and 2 tilde. They span a special three-dimensional subspace of the full Hilbert space. And this is the code subspace. So the code subspace in this case is three-dimensional. It's isomorphic to the single Qubit state that I'm trying to send. It is now embedded into a bigger Hilbert space, 27-dimensional Hilbert space. Very explicitly, this is the map. The 0 tilde is given by this combination of 3 Qubit states, and 1 tilde and 2 tilde can be defined similarly. And they're all rather symmetric. So this subspace is very symmetric between the 3 Qubits. No one Qubit is special, and each state is very entangled. And because they are very entangled, you can check that if we look at any one of these states, and in fact, any linear combination of these states as well, for any state that is built from these 3 states, the density matrix on any one of the Qubits, so suppose you trace out the second and third Qubit, and you just be left with a density matrix on the first Qubit, it is a maximally mixed density matrix given by 1/3 of 0, 0 plus 1, 1 plus 2, 2. What this means is that a single Qubit has 0 information about the message you are trying to send. You could be sending a very precise combination of 0 tilde, 1 tilde, 2 tilde. But if you look at just the first Qubit, you get 0 information. But that means that we have the remarkable property that we can completely recover the information from any 2 of the 3 Qubits. And to illustrate how this works, we can consider a special 2 Qubit operator as a unitary operator in U12. It acts just as permutations. So it just acts on the first 2, let's say the first 2 Qubits by doing this permutation, sending 0, 0 to 1, 1, 1, 1 to 0, 1, and so on. This is a table that you can write down. And then it's a homework problem to check that if you act this U12 on any of the encoded state K tilde on the previous slide, it gives back the message K on the first Qubit. So it decodes the information onto the first Qubit times some other universal state called the chi state. Chi state is this entangled state. And the point is that this works for any K. So in particular, if you form a linear combination of the K's 3 states labeled by K, you can still do the encoding, and the states that you are trying to decode simply comes back to the first Qubit. So this is a decoding map. It acts on an encoded state and gives back the message on the first Qubit. This is one way of doing the decoding. It only acts on the first Qubit, but as we said, all the Qubits are on similar footing. So by symmetry, you will also have other decoding maps that are located, supported only on the last 2 Qubits, or a unitary that is supported on the first and the third Qubit. So we have these decoding maps. Now, this is already pretty reminiscent of ABC puzzle that we said earlier. We have now 3 ways of decoding the state. You can think of A as 1, B as 2, and C as 3. But there's a difference in the sense that here we talked about decoding states, and previously in the ABC example, we talked about representing operators. But we can easily deal with this difference. We simply say that now we move on from decoding state to implementing operators in the following sense. We want to implement a single Qubit operator acts in the message as a 3 Qubit operator O tilde acting on the code subspace. So the idea is that O tilde acting on any state in code subspace should be how O acts on such a state. So it has the same matrix element as O has. You can actually find many ways of representing such an O in terms of O tilde. So there are many O tildes that does this job. O tilde is not unique. And the generic choice will be supported on all 3 Qubits. But then you can find very special choices. For example, by using U12, we can just choose a special O tilde that we call O tilde 12. What it does is to first use U12 to decode the state and put the message into the first Qubit, and then use O acting on the first Qubit to do whatever we want to do on the message, and then re-encode the message using the emission conjugate of U12. So this decode, act, and then encode procedure implements precisely what we want to do, such a code state. So O12 acts, by definition, O12 tilde is a state operator that only acts on the first two qubits, but it nonetheless implements this O operator on the code subspace. We can now define two other candidates for O tilde using instead of using U12, we can use U23 and therefore define an O tilde 23 that only acts on the second and third qubits. And similarly, we can define O tilde 13 that acts on the first and third qubit. So all of these three O tildes are good O tildes in the sense that they implement the same equation here. So they, but nonetheless, they are different operators. So say in a different way, these O3 tilde, these three O tildes are different operators in the fundamental theory in the 27-dimensional Hilbert space. But when they act on that special three-dimensional code subspace, they act in identical ways. So this holds for every psi tilde in the three-dimensional code subspace. So by using by using entanglement between three different qubits in the code subspace, we have reproduced a very similar picture as the picture we had before. So if we draw a picture, we would put the three physical qubits on the boundary of a circle, and they are roughly speaking corresponds to the ABC interval that we had earlier. And the three qubits are now local degrees of freedom on the boundary, and the encoded message that lives that we're trying to encode in the qubit model is the operator in the center of the bulk. So I've denoted it in the center. And different representations of the same centered operator, phi AB, phi BC, and phi AC, are simply these different O tildes, different realizations of the same underlying operation on the logical qubit. So they are the three different O tildes we saw earlier. And then the lesson is that, yes, it's not a problem that these three different phis are different CFT operators. The good property for them is that they need to act on the code subspace in the same way. And this is, in fact, the essence of subregion duality. We should think of subregion duality in this way. Subregion duality means that we're representing operators in an appropriate subregion in the bulk as a boundary operator on a subregion, but such representation only works on the code subspace. So this restriction on the code subspace solves the second puzzle. We can also solve the first puzzle in the same way. This is about the commutator that we mentioned earlier. And the solution is that we don't require this commutator to vanish in the entire Hilbert space. That would be in contradiction of the time slice X. We only require this to vanish in the code subspace. In other words, only when sandwiched by states in the code subspace, we require the expectation value of this commutator to be zero. To see this in the code, in the qubit code, well, we can, this is an operator between, this is a commutator between a bulk operator and the boundary local operator. In the qubit code, a bulk operator would be an O tilde. And a local operator on a boundary would be, for example, an arbitrary operator acting on the third qubit. I chose the third just because we want to talk about a specific local operator. You can choose X1 if you want. So the idea is if we sandwich, of course, the commutator generally does not vanish. You can check that. But if we sandwich it between two states, between states in the code subspace, then we can replace this O tilde by any realization we want because they all act in the same way on states in the code subspace. And in particular, we can make a judicious choice and choose it to be this O tilde 1, 2. And if we do so, the commutator between these two states then vanishes identically because the support is completely orthogonal to the support of X3. And by symmetry, we see that this works if we replace X3 by any local operators acting on the physical qubits. So in that sense, O tilde commutes with all local operators in the model within the code subspace. So that's okay. This solves the first puzzle. So we have now solved both puzzles by interpreting ADS-CFT as a quantum error-correcting code. And the code subspace in this case consists of states that are well described by local effective field theory in the bulk. We have to be able to talk about a local field here in order to describe a message being encoded in, for example, by a local operator here. And therefore, we're restricted to talking about bulk states where we can use local quantum effective field theory to a good approximation around this operator. And in particular, the Q-trit model now can be thought of as a toy model of holography, where we have an emergent Q-trit arising from the physical Q-trits in the problem. And this emergence only works in the code subspace. If we're outside the code subspace, then there is no reasonable message that we can extract, and there is no such emergent Q-trit. And the fun doesn't stop here. You can ask, what about states outside the code subspace? In the Q-trit model, the code subspace is only a 3-dimensional Hilbert space inside a 27-dimensional Hilbert space. So you can ask, what happens to the 24-dimensional subspace that is orthogonal to the code subspace? What do these states correspond to? And this is where gravity comes into rescue. These states, the 24-dimensional space of states, are the microstates of black holes. And these black holes are large enough that they have swallowed the bulk points that we're trying to encode. And so it doesn't make sense to talk about the bulk point in these states. And that makes sense because in the Q-trit model, when you are outside the code subspace, you don't think there is a well-defined, sensible message that you're encoding. And the point is so far behind the horizon that we can no longer account for it using local effective field theory. So that's the point. So let me quickly summarize what we have learned, and then talk about some recent developments and outlook. So far we have seen from the Q-trit model that we can how to interpret holography as a quantum error correcting code. And in particular, we solved the two paradoxes by restricting certain statements into the code subspace. We're not requiring commutators to be 0 for all states, but only for the code subspace. And that turns out to be an important ingredient to solve these paradoxes. And in particular, we can understand black holes as states outside the code subspace. So from all of this, we can derive many interesting results. I don't have time to discuss all of them in detail, but I'll mention a few highlights. And in particular, holography, broadly speaking, holography gives quantum error correcting codes that are not generic, that are rather new and special. In particular, they have to have a large number of degrees of freedom. This is how holography works. We take a large n limit, and with a large number of degrees of freedom, and that's the limit where a semi-classical description of gravity emerges in the book. So what is the structure of such large degrees of freedom in the code? What special structures do holographic codes have? This is a question that I think we're still exploring, and we know have found some answers to this question, but largely we are still trying to understand more structures in these codes. And one particular structure that we can immediately understand is that the code has the property that quantum information located further from the boundary, for example, things near the center, is better protected in such a code. The things in the center are not easy to corrupt. If you erase these green regions, you still can recover the bulk near the center. But if you have a message that is located very close to the boundary, then a judicious erasure near that part of the boundary will be able to erase the information. So it's less protected near the boundary. This provides a precise precise realization of the correspondence that radial direction in the bulk corresponds to energy scales on the boundary. And we can see this more clearly by trying to generalize the Q-trit model as well. The Q-trit model can be thought of as a very rough, coarse-grained version of holography. We have essentially coarse-grained all the bulk physics into a single point, in fact, into a single qubit, three-dimensional Hilbert space. We have reduced all the boundary physics into 3 points. So it's very rough. It's a rough toy model of holography. But then one can build more intricate models of holography by having more bulk points and having more boundary points and build these tensor networks. And they've also realized ADS, they're also toy models, but they are more intricate toy models of ADS-CFT. And in this case, you can see that things in the center are more protected than things near the boundary, very precisely. And there's a lot of similarity between ADS, CFT, and tensor networks. And this has motivated us to look for more properties of holographic code. But now we understand one thing, at least, that holographic codes somehow can be decomposed into codes with a flat entanglement spectrum. I don't have time to go into the detail, but this is a very special property, not, for example, satisfied by arbitrary tensor networks. You can imagine building up a tensor network with non-maximally entangled links, and that wouldn't satisfy this kind of property. Gravity somehow is very simple. Correspondingly, a holographic state can be decomposed. This is a simple decomposition as the decomposition of the code here, but the state can be decomposed as superpositions of fixed area states. And these states have flat entanglement spectrum. And it turns out these fixed area states are better analogs of tensor network states. So there's a direct analog where you consider gravitational state where you fix the area of this surface, and that is a very good analog of what you get out of tensor networks. We can also ask how large the code subsets can be. In other words, how many states can we realize the algebra of bulk operators? And this answer is given by a general theorem in quantum error correction, which basically matches the idea that if you try to get more and more states, then eventually it becomes it corresponds to a regime where we make a black hole. And it turns out the counting is precisely given by the black hole entropy that scales with the area. So it's very nice to see that this correspondence comes out. And this, in fact, makes the precise and earlier point that I mentioned, that if you try to, in gravity, when you try to define local observables very precisely, eventually you get to a point where things collapse into a black hole. And here you can see that fairly precisely in the code language. And it's useful to mention that if we don't have black holes, then we would really have paradoxes. We wouldn't be able to resolve them, and there would be real contradictions. So it's only when we have quantum gravity that has black holes that we can actually have a higher dimensional effective theory emerging from a lower dimensional one. And reinterpreting ADS holography as a quantum error correcting code has also been made it possible to reconstruct bulk physics in situations more than the Ringler reconstruction. So I talked about Ringler reconstruction, but it turns out there is a more powerful version of this, which goes under the name of entanglement wedge reconstruction. And it turns out that proving this required useful input from quantum error correction. And the good thing about this is that entanglement wedge reconstruction reaches deeper into the bulk than a version of the Ringler reconstruction or causal wedge reconstruction. And in particular, it has the potential of going beyond the horizon. So this is not possible using previous understanding, and I really think of this as a conceptual change. And I just mentioned that there are many aspects of a fascinating connection between entanglement and spacetime geometry, including ER equals VR and the real Takayama formula, which I don't have time to go into the detail to. And quantum error correction story fits very nicely with all of these topics, and in fact has a very strong connection with the real Takayama formula. But we're really still learning about interesting lessons about these holographic codes. And just as an example, a recent proposal is that such codes must be non-isometric. in the context of probing physics inside a black hole. And roughly speaking, the idea is that the inside a black hole has too many states to be encoded isotrophically as a CFT state. So we need to do some non-asymmetric encoding. And finally, let me come back to our universe. We don't yet have a holographic framework for describing quantum gravity non-perturbatively in accelerating universes such as our universe. But I think one promising direction is to take what we learned today, the ADS-CFT lessons that we learned today, but take those lessons outside the ADS box and apply them to more general spacetimes. And so far, a result that is surprising in some sense is that in the context of de Sitter space, there seems to be a maximally mixed, maximally entangled structure between causal patches of de Sitter space. But I would certainly be inclined to say that we still have much more to learn. And let me just end with the observation that gravity is not just a quantum aircraft code, but it's such a good one that we don't even realize that there could be errors. We live in a world where gravity is in principle working as a quantum error correction code. But we have so far not detected any deviation from, well, we haven't detected any direct evidence of error correcting feature experimentally. Maybe we can detect them someday. But because it's such a good code, maybe this will lead to new discoveries in unexpected areas. So let me close here and thank you.
So let's a few questions.
Is a black hole considered as a specific or it's considered the evaporation?
In this context, I was just talking about the black hole at a fixed time. So it doesn't really matter whether it evaporates later on or not. I didn't talk about the evaporating story. One can, in principle, try to do evaporating black holes in this context as well. But in the picture I just drew, where I said the black hole states are the 24-dimensional Hilbert space outside the code subspace, that was just a black hole at a given time.
So do you mean that quantum gravity has a low-dimensional holographic field theory or just for the digital case?
Are you asking, so just to make sure, I think you're asking whether in the de Sitter case, we expect quantum gravity to be holographic. So I personally certainly expect quantum gravities to be still holographic. There are many ways to think about this. There is actually a proposal which goes under the name of DS correspondence that says that there is a way to think about the Sitter space in D+1 dimensions as a theory of a lower dimensional de Sitter space coupled to a particular kind of matter sector. But more broadly, I think one way to think about this is that we have ADS-CFT that says in ADS, quantum gravity is holographic. We have matrix models that says in certain other contexts, non-ADS-CFT contexts, it's also holographic. And we have evidence sometimes that flat spaces could be holographic as well. So there's no reason that de Sitter space could be different.
Also, I want to ask, do we have any other further research on the logical operator in the CFT code? Specifically, my question is, like in the homological code or stabilizer code, which have recently intensive studies on the logical operators for tolerant universal quantum computation. These operators, they are also important to solve your first paradox. So I want to know, is there any recent research further like what happens for the stabilizer code?
So there are different kind of codes we can talk about. I want to point out, maybe not in the context of stabilizer code, but there is a different kind of code provided by random tensor networks. So so it's different from the tensor network pictures I drew. It's not using perfect tensor, but rather random tensors. And in such a context, one can get essentially a lot of the features of holography, including the RT formula and also bulk reconstruction and so on. And so one recent, I'll mention one recent development in that context is that with my students, we've been able to add edge modes into such a random tensor network. And the goal is to mimic a gauge field, a gauge symmetry in the bulk, because gravity is a gauge symmetry, and it has many consequences in such a code. And if we look at a random tensor network, we can also put in the gauge symmetry into the bulk and find essentially a kind of improvement over the original random tensor network. And just to make connections to the stabilizer codes mentioned, there is a paper recently about that in stabilizer codes that it's impossible to have a central algebra that would center, which would have a center in the case of a gauge field. So in that sense, we need to go beyond stabilizer code in order to understand what is a better toy model of quantum gravity.
Mark, the question is, it's like how we give a new person see the idiocy in the quantum error correction perspective. My question is, can we use the idiocy or holographic field to design a quantum error correction code like Qtrait? How the ideas in the idiocy can guide us to design one good code for quantum error correction?
Yeah, I think to some extent we have already done some of that. And for example, the tensor network is really motivated by understanding ADS-CFT as a quantum error correction code. And then people try to build models of such codes that are inspired by ADS-CFT. So these tensor networks is basically one way of doing that. And they are quantum error correcting codes. Of course, one can then ask what other codes one can build motivated by ADS-CFT. And I think one of the things that we haven't explored very much is in the context of non-asymmetric code. So what particular structures and what new kind of non-asymmetric code that we can write down that has some of the properties of holography. So I think that could be one of the future directions to try to understand.
Thank you.